We're going to talk about what is probably one of the most important applications of dot product here, which is projections. So the idea of a projection is a very general idea, but in this class we're just looking at a specific example of projecting one vector onto another vector. So if we have a non-zero vector, A, and we have another vector, B, we want to ask the question, how much of B is going in the direction of A? In other words, another way to put it is, what is the shadow of B onto A? How much of it is going just in that direction and not any other direction? So we call this the vector projection of B onto A. So what I'm going to do here is just draw a little picture and show you exactly what I mean about what's going on here with A and B. So here's two vectors A and B. So what we mean by how much of B is in the direction of A, what we mean is if you had to get to the tip of the vector B, and you're starting here at their common initial point, and you had to go along the direction of A, how far would you go before you decided, well, okay, I'm going to stop now, and now I'm going to go to the tip of B. So the question here is saying, how far would you go along? And I think everyone would agree that what you want to do is go along to the point where you would be right at a 90-degree angle from that tip. Right, that's going to be your most efficient route. If you're going along vector A, you want to go right until the point where you're at a right angle from the tip, and then you want to go straight up to the tip. In other words, what we're doing is really dropping a perpendicular down from the tip of from the tip of B down to A. So what we've done now is we've got two vectors. We got this vector here, out to here, and then we've got another vector that goes up to B. So this vector that goes out to this point here, I'll do it in a different color, this is what we're going to call the projection. So this is the projection. So we're going to denote this projection of B onto A. So it's going to be a little subscript with A and then B. And then the other vector that we have here, we'll have a name for this in a minute, but let's just call it something else. Let's just call it the difference of these two. So we have the other one going up. This vector here then has to be B minus the projection of B onto A. Okay, so we've split up B into two pieces, basically. A way that we could write this would be to say that our vector B now we have written as this projection part plus what's left over, which is B minus the projection. Now what we're going to do is look at this geometric picture, and we're going to try and figure out if there's a way we can get a formula for this. So this is called the projection, or the vector projection. The projection of B onto A. So how can we come up with a formula for this? So what we're going to do is note a couple facts, and these facts are going to lead us in terms of the dot product into what the formula has to be. So let's list some facts here that we know. So here's two facts. And this is just from looking at the picture. Certainly the projection should be in the direction of A. So the projection of B onto A be in the direction of A. So that's one kind of piece of evidence here. The other piece of evidence we're going to have is that this red vector, what's left over, notice that that's orthogonal, right? There's a right angle here. So that red vector is orthogonal to A. So B minus the projection, the stuff that's left over, should be orthogonal to A. So what we have to think is, how did these two geometric facts translate in terms of algebraic properties of vectors? Well, what does it mean to be in the direction of A? Well, all the vectors that are in the direction of A, those are exactly the scalar multiples of A. So we can translate the first fact as saying that the projection of B onto A needs to equal needs to equal c times a for some scalar c. It has to be a scalar multiple of a. Now that scalar might be positive, negative, or 0. It could be anything, but it has to be some scalar. What about the second part? It says that this vector here, the vector difference between these two, should be orthogonal to a. Well, we already said orthogonal means the dot product is 0. So let's just write that down. B minus projection of a onto b dotted with a is equal to 0. So these are the two algebraic facts we have. So all we have to do now is put these together, and by putting these together, we'll be able to come up with an algebraic definition of what this projection should be. So let's go ahead and do that. So the key is going to be to take this c times a, which we know is an expression for the projection, and substitute it in here. So we're going to substitute there. So what do we get when we substitute that? So we would get b minus c times a dotted with a is equal to 0. Okay, well, we can do some stuff with that. If we distribute, so now you have to remember all the algebraic properties of the dot product that we did. Remember how we said the dot product basically allows you to FOIL stuff out like you would normally do in ordinary algebra. So we could FOIL this out and get b times a, and actually I'm going to switch them here because the order of the dot product doesn't matter. So I'm going to say a times b minus c times a dot a is equal to 0. Okay. But now I could add the second term, add the c times a dot a to both sides. So plus c a dot a plus c a dot a. So these two terms will go out. And what we're going to get is we're going to be able to solve for c. So maybe if that first step wasn't clear, this is what we were doing before. We were distributing here. Okay, but now we can solve for the scalar c, because we have a dotted with b is equal to c times a dotted with a, and then I can divide by a dotted with a. Okay, so why does it help to have c? We figured out what c is. Great. Well, go back up here. Remember, it said the projection was a scalar multiple of a. Well, we found what that scalar is. So the point is now we can go and substitute back into 1. And there's where our formula for the projection is going to come from. So substitute back into 1. Finally, we get our formula. The projection of b onto a is equal to c times a, so it's equal to a dotted with b divided by a dotted with a, and it's that scalar multiple times the vector a. Okay, so this whole thing in parentheses here, let's not get confused about what's a vector and what's not. The a on the outside here, outside the parentheses, that's a vector. And then everything in parentheses, there's a lot of vectors in there, but it's just a scalar. It's just saying one dot product divided by another. So this is just telling you the projection is this particular scalar multiple of a. Let's look at an example. Okay, we're going to find the projection of 5, negative 2, so 5i minus 2j onto 3i plus j. This is just in two-dimensional vectors, so we're just keeping it really simple, mainly so I can draw a nice picture here. Now, let's draw a picture first, actually. So, and let's do this without the software, without going to a website, because this is simple enough to graph that I think we can actually get a good idea of what's going on without resorting to going to one of the websites. Okay, so that's pretty good. There we got xy. All right, so b would be 5, -2. If this is anywhere close, then we should be able to get at least a rough idea of what the projection should be. So here's our vector b, the 5, -2. Goes out like that. And I'm projecting onto 3, 1. So 3, 1. So let's draw what this should be. So what we should be able to do is take the tip of b and project onto a. Now if you notice here, since a only extends so far, we actually need to extend this in this direction. So this is actually going to go out, let's see, it would go out to 6, 2, which would be about there. So it's going to go out, I'll just make a dashed line here. So the projection doesn't have to project onto A, but it projects onto the line determined by A. And then it says take the tip of this B and take a perpendicular over to this line. So that's going to be something like this. Okay, yeah, about like that. See how that's about 90-degree angle. That meets at a 90-degree angle there. So we start here, we drop down a perpendicular. So the projection is about equal to this. So this is the projection vector. Projection of B onto A. Now, what does that look like about? I don't know. I mean, it's A was 3, 1, so this one looks like it's maybe 4 something. So it's like 4 and then a little bit bigger than 1. So it's in the same direction. It's just a little bit scalar multiple bigger. So let's actually compute it now and see if we can figure out what this equals exactly. Okay, so it's A dot B over A dot A. Scalar multiple of A. So A dot with B, we can do this. The one reason I chose a two-dimensional one, so it's easy to visualize and it's also really easy to compute here. So 5 times 3, 15 minus 2 over A dotted with A is going to be 3 squared, 1 squared, 9 plus 1. So all that times A, which is 3, 1. So that's 13 over 10 times 3, 1. So it's going to be 39 tenths, 13 tenths. And since it's tenths, I could also write it as a decimal if I wanted to. It's 3.9, 1.3. So about what we were saying. The I component is a little bit, it's about 4. It's a little less than 4. And the J component is about a little less than 1 1/3. So 3.9, 1.3. Matches perfectly with our picture. All right, before we go any further, there's several comments I should make because there's some common mistakes people make and there's just some observations that need to be made about this. So there's a lot of these, so I'm just going to number them. So first thing, projection of B onto A is a vector, not a scalar. There is such a thing as scalar projection. It's a component, which is the norm of this, the length of this vector, but the projection itself is a vector, not a scalar. Okay, second point. Note that the vector that you're requiring, the vector that you're projecting onto has to be non-zero, can't be 0. Now you want to think about, well, why is that? So if you want to pause the video, think about, why does the vector A have to be non-zero? Okay, so the reason A has to be non-zero is we're trying to figure out how much of B is going in the direction of A. If A was 0, it didn't have a direction. Okay, so it doesn't make any sense to say how much of it is in a certain direction if the direction's not defined. Now, another way you could say this a little bit more concretely is if you just look at the formula you're supposed to divide by A dot A. So the zero vector dotted with itself is going to be 0. You can't divide by 0. So that's more of a concrete algebraic reason. The geometric reason is the zero vector has no direction, so it doesn't make any sense. But notice b equal to 0 is okay. In other words, you can find the projection of the zero vector, and in fact, it's going to be 0. Doesn't matter what you're projecting onto. So the projection of the zero vector onto any other non-zero vector is always the zero vector. And you can verify that from the formula. You should think about why that's true. Third, people get real mixed up about is it a multiple of A or is it a multiple of B? It's always a multiple of the vector you're projecting onto. So the projection of B onto A is a scalar multiple of A, not B. That's probably the most common mistake, I would say, in doing the formula. So the formula that we had above was A dot A over A dot B, scalar multiple of A. The most common mistake is to take the scalar multiple of B. So you just get A and B mixed up. The second most common mistake, I think, would be to divide by B dotted with B instead of A dotted with A. So in either case, the mistakes are usually switching A and B or getting A and B mixed up. They're not the same. You really have to keep track of which is which. Okay, another thing. If we fix A not equal to the zero vector, then this expression, projection of B onto A, is a vector-valued function of B. So a vector-valued. In other words, you give me a vector, I'll give you out a vector. So in other words, it's a function from R2 to R2. Or if it was 3 dimensions, it would be R3 to R3. In fact, there's a name for this. It's called a vector field. So technically, if you fix the vector that you're projecting onto, you get a vector field out of it. Number 5, this is super important here. If the angle between A and B is obtuse, in other words, the angle is bigger than 90 degrees. In that case, we know that the cosine of an angle bigger than 90 degrees, or between 90 and 180, is less than 0, right? It's between -1 and 0. So that means that the dot product A dot B has to be less than 0 if you think about the formula for the cosine, where the A dot B is in the numerator there. So that means that dot product has to be less than 0, which means that the projection is a negative scalar multiple of A. Okay, it's really important. If A and B have an angle bigger than 90 degrees between them, then the projection of the one onto the other will always be a negative scalar multiple. In other words, it's not going to point in the same direction, it's going to point in the opposite direction. So it's the same direction in the sense that it's still on the same line, but it's pointing in the opposite direction. Negative scalar multiple of A. Number 6. If A is a unit vector, so remember what a unit vector is, that means A has length 1. Well, if A has length 1, that means that A dotted with itself is 1. Then the formula takes a nice form. Then the projection formula just becomes projection of B onto A is equal to A dot B times A. In other words, it's just a scalar multiple of A, and the scalar multiple is you just dot it with A. And that's how you find what that multiple is. So there's no divided by A dot A because A dot A is 1. One more comment here. So there was a lot. If B is itself a scalar multiple of A. Now think about what the projection should be. If B is entirely a scalar multiple of A, then all of B is in the direction of A. All of it. There's nothing that's not. Which means the projection of B onto A should just be itself, because everything about B is in the direction of A. And that is the case. So if B is a scalar multiple of A, then the projection of B onto A is just equal to B itself. And again, you should take a minute to check this. This is actually something you can prove. Think through why that's the case. Also, if A and B are orthogonal, if B is orthogonal to A, now let's think about what this should be geometrically. If B is orthogonal to A, none of it is in the direction of A. Well, if none of it is in the direction of A, the projection should be 0. Should be the 0 vector. And that is the case. If B is orthogonal to A, then projection is 0. And again, you can look at the formula for it, and you should check to see that that really is the case. Okay, so that's a lot of comments, but you should think about each one of these comments here. I know it's a lot, but if you really understand all these comments, it'll really help you understand what the projection is and what it does. So now we're going to talk about the scalar projection, or it's called the component. And I actually need to go back and I need to change this in the notes. So I'm going to make a little bit of change here. I wrote that it's the magnitude of the vector projection of B onto A. That's almost true. So it's actually the signed magnitude. What do we mean by signed magnitude? Well, it means if it's pointing in the direction of A, then it's going to be positive. If it's pointing the opposite direction, it's going to be negative. So it's the magnitude up to plus minus sign. So to see what this should be, let's look at the formula for the vector projection times A. So what I'm going to do here is I'm actually going to separate out a unit vector. So what I want to do is take A and multiply and divide by its length. Okay, so we're going to have A dot B over A dot A. Now what I want to do is really normalize A. So I want to divide by the length of A. But in order to do that, I need to multiply by the norm of A as well. So I'm going to multiply by norm A. And then, so that's another scalar. And then A over, okay, so the idea here, hopefully this makes sense, is I want this to be a unit vector. So this is a unit vector in the direction, it's in the same direction as A. Okay, well now let's look at what's left over, all this stuff over here. Okay, so I've got A dot B. Now I'm going to write the A dot A a little different way. A dot A is equal to the norm of A squared, but then I've got times the norm of A. And this is again all times this unit vector. Notice that I can cancel. That cancels. So all that I'm left with really is this kind of scalar out in front, and then this unit vector here. Got A dot B over length of A times A over norm A. Now, again, this is a unit vector. This A over norm A is a unit vector in the same direction as A. So that has length 1. So the length of the projection vector up to sign is this. The only difference is this is the same as the length of the projection, except it could be negative. In other words, I'm not taking the absolute value. So this is plus minus. It's either plus or minus the length of the projection vector. So that's what I mean by when I said it's the signed magnitude. Basically what it's doing is it's saying, look in the positive direction of A. So A determines a positive direction. Think of that just now like a number line. We're just going to count off how many units we go. So let me go back up to the picture here. Maybe this is a better way to explain it. If we go all the way back up to the picture here, what the scalar projection or the component is saying start right here at this point, and then this just determines a number line going off to the right, which is the direction that A is given, right, going off this way. There's a positive direction, and there's a negative direction. There's a negative direction over there. Just start it here like it was an origin, and just see how many units, how many signed units do I have to go to get to the tip of the projection vector. So like on this number line, how far do I have to go? If it's positive, then it's in the same direction of A. If it's negative, it's in the opposite direction. That's all that the component is measuring. So this thing here, that's the component. I'm kind of running out of space here, just a minute. So now we're going to talk about the orthogonal projection. I don't really like this terminology too much, but it's the one that our textbook and homework assignments use, unfortunately. So just to not cause confusion, I'm going to use the same terminology. So this vector is what's left over after you've done the vector projection. So if we go back up to our picture up here, the very beginning, it's this here. That's the orthogonal projection. It's the B minus the projection of B onto A. It's the second piece of what we were talking about. So we're going to define this here. This is going to be defined to be, so the notation our book uses is, and this is actually just in a homework problem, it's ORTH. I don't like this notation either. I kind of like perp, P-E-R-P, because it says like the perpendicular part, but whatever, I don't get to choose the notation the book uses, so I'll call it this ORTH for orthogonal. So this orthogonal projection then is B minus projection. Okay, that's a definition. And then that equation that we had above, I'll rewrite it here. That's what's called the orthogonal decomposition of B. So when we write B is equal to its projection onto A plus this orthogonal part this is the orthogonal decomposition right here. So again, this is easier to understand with an example, so let's look at this particular example. So here A is 12, 1, 2, and we're going to find the orthogonal decomposition of B, which is negative 1, 4, 8. Okay, so what do we start with? We start with finding the projection. Projection of B onto A is A dot B over A dot A times A. All right, so that is going to be, A dot B is going to be negative 12 plus 4 plus 16 all over A dot A, 144 plus 1 plus 4. Okay, what is that going to make? 8. 20 minus 12 is 8 over 149. Okay, that's not super nice, but whatever. 8 over 149 times 12, 1, 2. So that's 8 times 12 is 96. So 96 over 149, 8 over 149, 16 over 149. Okay, that's the projection. That's the first piece. Now we need what's left over. So this is going to be B minus that. Okay, so that's going to be -1 for 8 minus this 96 over 1. All right, so this doesn't work out to any particularly nice numbers. Let's see. Okay, so it turns out to be this. What I'm going to do is I'm going to box this, and then I'm going to give you approximations like to 2 decimal places, because these are just kind of awful fractions. Okay, so there's their approximations. And now, these should be orthogonal, so we should be able to check that these are orthogonal. So one way you can do this is to take 96, so we want to take 96 over 149 times minus 245 over 149 plus 8 over 149 plus 16 over 149 times this. Okay, so if you do this, first of all, notice that it's just something over 149 squared. And what you should get if you do 96 times -245 plus 8 times 588 plus 16 times 1176, you should end up with 0 there. So you can check that that's just 0. Now, that means that they really are orthogonal. So I checked those, I multiplied them out, or I took those products and added them up, I got 0. So these are orthogonal. Okay, so I'm going to show you these vectors. So what I'm going to show you first is the vector that we're projecting. So this is -1 for 8. Okay, so you can see that -1 for 8. And we're projecting onto the vector 12, 1, 2. So let me show you 12, 1, 2. Okay, there's 12, 1, 2. Let me move it around a little bit so you can see. And let me get rid of the box. We don't need that. Okay, so there's 12, 1, 2. Okay, so let me show you the projection. So the projection vector was this 96 over 149, 8 over 149, 16 over 149. So before we do that, think about projecting on. And notice these two vectors are almost orthogonal. Not quite. But think about what it's going to look like. I'm going to try and figure out how much of this vector pointing up is going in the direction of this one kind of going off to the left here. Not very much of it. So here's how much of it there is. Okay, that's it. So see that? So if I drop a perpendicular from this one up here all the way down, I only get that very little one. And I can even zoom in here. You can see it's a very small piece. And now here's the orthogonal part that's left over. You can see it here. -245, 588, 1176. There's that piece. So I graphed that vector with the initial point there so you can see the sum. So there you can see the sum. See, it's got the one projection part that's very small in the direction of this, and most of it is in the orthogonal direction that you can see there. I maybe should have chosen 2 examples that had a little bit more equally balanced parts, but I ended up getting one that was mostly orthogonal and not in the same direction. All right, one last application. I know this is a long section, but it's a super important topic. One application of projections that comes up a lot in physics is calculating the work done by a force when the force is not being applied in the same direction as the motion. So the most basic example of force is you're just applying a force in a direction. You just multiply the force times the direction to get the work. So in general, in physics, the work done is equal to the force, the magnitude of the force applied, times the distance. However, if the force is being applied in a different direction, then you don't want all the force. You only want the part of the force that's going in that direction. So for instance, let's say that I'm pushing something uphill. Okay, so there's like a cart here that I'm pushing uphill. And this is the force here. But it's going in this other direction. So like I'm pulling it at an angle here. Let's call this theta. And let's say that we apply this force to move this object from point P up here to point Q. Okay, so up to there. Now let's call this vector D. So D is going to be PQ for distance. So we're starting with this object at point P, moving it along to point Q with this vector F, this force applied at an angle theta. Now, we don't want to multiply the magnitude of F by the magnitude of D. What we want to do is take what's the piece of F that's going in the direction there. So that's going to be given by F, the norm of F, times the cosine. So the force times cosine theta, this is the component of the force vector along D. Okay, so this is the actual force that's applied in the direction. It's the magnitude of the force that's applied in the direction. So what we need to do is really multiply this quantity by the distance traveled, which would be the length of D. So the total work done is actually going to be, in this case, this component, so this magnitude of the force that's actually going in that direction times the length of D. But notice that is exactly the same thing as F dotted with D. So here's another nice interpretation of the dot product. If you think of you're taking the dot product of a force vector with a distance vector, then the dot product represents the total work done by that force in that direction of D. So you can think of it as the norm of the force times the norm of the distance times the cosine, or you can just think of it as the dot product of the two vectors. Okay, so let's look at an example. A sled is pulled along a level path through snow by rope. Okay, so here's pulling it. 40 degrees. Okay, so let's do, there's 40 degrees. Okay. And the force here, 30-pound force. Okay, so force. And here's the sled. I'm not very good at drawing sleds. I don't know, maybe it's something like that. So there's our sled. So we're moving it this way. And we do go 80 feet. So let's say all of this is 80 feet. Okay, so we're going to find the work done. Oh, and it's also, here, label it, 40 degrees. So the total work done, F dotted with D, is the norm of F, cosine theta, length of D. So in this case, it would be the 30 pounds times cosine 40 degrees times, now this would be, here, this would be the D, from the starting point of the sled to the ending point of the sled would be D, and that's 80 feet. So the units we get here are foot-pounds. So we get 2400 times cosine 40 degrees, and the units are foot-pounds, which is approximately equal to 1,839 foot-pounds. So that's to the nearest foot-pound. Okay, so that's a very nice application of components. This is a really common kind of physics problem. So in the next section, we're going to be talking about the other major operation on vectors that we need to talk about, which is only defined for three-dimensional vectors. That's the cross product. And cross product is very much related to orthogonality.